Human beings need energy to live. We need energy so our bodies can grow and stay warm. And our muscles need energy so we can move around. But where does all this energy come from? Toys and machines won't move unless you give them energy. When the battery runs down, this toy dancer will stop moving. Living things are no different. Human beings don't need batteries, but we do need to eat and breathe to stay alive. Eating and breathing are vital because they supply us with energy. Chocolate is a high-energy food because it has a lot of fat and sugar in it. Sugary foods give you energy very quickly. Other foods are more useful for building up your body than for giving you energy. Bread contains starch, which is another good supplier of energy, so a sandwich is a good snack for a dancer. All the kinds of foods you can see here have different amounts of energy depending on what they contain. The highest energy foods contain sugar, starch, or fat. But you don't have to guess how much energy is in food. You can measure it. We'll be back after this commercial break.
Butter, margarine. Which has got more energy? We asked some shoppers.
Excuse me, sir. Can I ask you a question?
You can, yes.
Which do you think has more calories, butter or margarine?
Butter.
Everybody would say butter, wouldn't they? But I don't know.
Yes.
Well, go on then, I'll say margarine.
It could be margarine.
Butter.
Butter.
Butter, really.
Butter.
Butter?
So butter gets the vote on energy. But we weren't so sure. So we did a scientific experiment.
We took 1 gram of margarine and placed it in a crucible. Then we added a fuse so we could set fire to it. Yes, you can set fire to margarine. Everything was sealed in a steel container, with a thermocouple in the top to measure the temperature. Then we let in some oxygen for better burning. The burning food releases heat energy, which warms up the steel container. The final temperature of the container is a measure of the total energy in the margarine. A gram of margarine contained 30.0 kilojoules of energy. A gram of butter had 30.3 kilojoules.
So, our tests prove that butter and margarine have almost, but not quite, exactly the same energy content.
How much energy is there in a peanut? Design an experiment to find out. We're not going to tell you how to do it, but there were some clues in the commercial you've just seen. It takes about 1 kilojoule of energy to lift someone over your head. How many peanuts would you have to eat to do it? The harder we exercise, the more energy we need. So why does exercising make us breathe more heavily? There must be something in the air that we need to produce energy. When we exercise, we need more of it. You might have guessed already that breathing supplies us with oxygen. Breathing's so natural that we do it without thinking. It's controlled by the diaphragm muscle, which can be found just beneath the lungs. When we breathe in, the diaphragm moves down and the ribs move out, leaving room for the lungs to expand. This lowers the pressure inside the lungs, so air rushes in from outside. When we want to breathe out, the diaphragm pushes upwards, squeezing the lungs and forcing the air out again. Singers learn to control their breathing using the diaphragm muscle.
Green trees are bending, poor sinner stands a-trembling. The trumpet sounds within my soul. I in God long to stay.
This is a bottle of lime water. In ordinary air, lime water is completely clear. But it changes if you breathe into it. As the dancer exercises and breathes out, the lime water goes milky. This is a sign that the gas carbon dioxide has been produced. Ordinary air is a mixture of several different gases. About 80% of the air in the atmosphere is nitrogen. Most of the rest is oxygen, and there are very small quantities of other gases. But we know that the air we breathe out has enough carbon dioxide in it to make lime water go milky. Breathing converts some of the oxygen to carbon dioxide. For one gas to change into another, a chemical reaction must have taken place. The reaction that takes place inside the human body converts oxygen to carbon dioxide and also produces energy. We've already seen that you can get energy from food by burning it in oxygen. It can't be burning that goes on inside a human body. So what really happens?
Here, in Leeds, a figure lies comatose in desperate need of respiration. And I think, yes, oxygen is ready to come into the lungs, so I'm just going to get out of the way.
The first stage in the rescue operation is breathing in. Oxygen is vital for respiration, and it looks like they're getting plenty into the lungs. And now, the red blood cells swing into action. This is a matter of life and death. They've got to get that oxygen to where it's needed, in cells all over the body. As well as oxygen, it looks like they're picking up some nutrients. No wonder the red blood cells are known as the best aid organisation in the world. This one's headed for the leg. That's good news. Those muscle cells will be desperate for energy. The red blood cells bring in oxygen and glucose. That's a sugar the body makes by breaking down food. She's handing over oxygen and glucose and getting something else back. This must be a reaction. Yes, The reaction has produced carbon dioxide and water. And the leg cells found some energy. Glucose plus oxygen gives carbon dioxide, water, and energy. That's the one we're looking for, the respiration reaction. But now they've got to get rid of that carbon dioxide. My guess is it's going back to the lungs. Yes, not only do they take oxygen from the lungs, they bring back carbon dioxide. And now the red blood cells are ready to pick up more oxygen and nutrients. Glucose and oxygen are needed everywhere. Then respiration can give the muscles all the energy they need. No wonder that heart's pumping. These red blood cells look like they could go on forever. They'll have to get some oxygen to the brain. Even thinking needs a bit of energy. The carbon dioxide's really building up in the lungs now. They must make room for more oxygen. Time to breathe out. These lungs are designed to take as much gas as possible, but it's oxygen you want in there, not carbon dioxide. The brain cell's getting busy now. There's plenty of energy around while they're waiting for the next breath.
So there you have it, respiration. This is Katie Aid reporting for Scientific Eye, Leeds.
Thank you.
We need glucose and oxygen so that respiration can take place. Why do some foods give us energy more quickly than others? And what happens if we exercise so hard that our breathing can't keep up? Can respiration still provide us with enough energy?
The insect mouthparts are routinely categorized into 4 sections. There is the lower mouthpart, or mandible, and there are 2 to it.
What was that? Everything we saw and felt and heard was energy being transferred. Energy stored in concentrated form in explosives has been released and transferred as light, a shockwave, heat and sound. So what is energy transfer? Energy transfers from higher energy levels to lower energy levels. Energy cannot be created or destroyed. The total amount of energy remains the same. As it transfers from a high energy level to a lower one, it spreads out and becomes less concentrated, less useful. Can you think of any examples? There's concentrated energy stored in that weight, potential energy. The higher it is, the more potential energy it has, due to gravity. How could that energy be transferred to another system? Watch the waves. Now everything's gone quiet. If energy can't be created or destroyed, where's it all gone? When the weight was dropped in the tank, some of the potential energy was transferred as sound, in moving the water, in raising the level of the water in the tank, even as heat, and the sum total of all this diluted energy is equal to the potential energy that was concentrated in the weight. When energy transfers from a higher level to a lower level, it makes things happen. Now the energy has become less concentrated. It's still there, but it would be difficult to detect or measure it. When energy transfers from a high level to a low level, it can be used to do work. It takes a lot of energy of movement, or kinetic energy, to wind up the crossbow. Where's it going? Some of it is transferred as potential energy, stored in the flexing of the bow, ready to be transferred back to the arrow as kinetic energy. We've just seen a series of energy transfers. Could you list them? A lot of kinetic energy is transferred to the bow as potential energy. Some of that potential energy is transferred as kinetic energy to the arrow. Some of the kinetic energy in the arrow is transferred to the air while it is in flight, but most of it is transferred to the target, until finally the energy is so spread out, so dilute, that it can no longer be detected or do very much. Nobody knows exactly what energy is, but we can usually tell when energy is being transferred, because energy transfer makes things happen. Here's potential energy stored in fuel, being released in a chemical reaction and transferred as light and heat. How is energy being transferred here? Or here? Or here? What's happening here? How is energy transferred in a Clockwork Mouse and in a Ginger Tom? What do all these processes have in common? As concentrated energy becomes more dilute, it can do useful work. What work is being done here? Almost everywhere you look, you'll find energy, or energy being transferred, even in a cup of cold cocoa. The cocoa particles are moving. They're being knocked about by even tinier water molecules, which have kinetic energy, like the arrow we saw earlier. This is called Brownian motion. Now what's happening? The kinetic energy of the water molecules was increased by heating the cocoa. What would happen to the molecules if you left the cocoa to cool? The movement of the cocoa particles slows down because the water molecules have slowed down. What would happen if the temperature kept on falling? A difficult question. In the meantime, let's see what's in the fridge.
15 degrees Celsius and falling. 10 degrees Celsius and falling. -10 degrees and stable.
Ice. Water in crystal form, with all the water molecules locked into a three-dimensional lattice. The molecules aren't moving around much, but they're constantly vibrating. They have a small amount of kinetic energy. What happens if their kinetic energy is increased? This represents a solid. A liquid and a gas. What does that tell you about the relationship between kinetic energy and the differences between solids, liquids and gases? In a solid material such as ice, molecular movement is limited. Solid objects keep their own shape because the molecules stay in place, vibrating. If we add energy, the speed of vibration increases and breaks the bonds between the molecules that hold the solid together. They mix and mingle. The solid becomes a liquid which takes up the shape of its container. What happens if we add even more energy to the system? If we add enough energy to the system, the liquid turns into a vapor which fills the container. This relationship between temperature, structure, and kinetic energy can be made to do work. Any idea how? This lump of metal doesn't look as if it's going to do anything, but add a little heat energy and the water in the boiler turns to steam. The molecules of H2O in steam contain a lot of kinetic energy. As they collide with the walls of the cylinder, they exert force on it. The kinetic energy in the steam is transferred to the piston, driving it down the cylinder. And what has happened to the H2O molecules? Finally, the movement of the piston is transmitted to a wheel, which could be used to do work, such as drive steam engines. high-pressure jets of water. Drive a lorry. Or turn a carousel. Welcome to William and Doris Carter's traditional steam-driven mobile fair. Every ride in the fairground is powered by a coal boiler turning water into steam. Which drives the machinery. Which does the work. Although the customers probably think of it as play. But enough of this frivolity. Now we'll look at a more serious use of steam, such as lifting an upright piano. Here, the kinetic energy in the steam engine is being transferred to the piano as potential energy. The higher the piano, the more energy it has. Could that potential energy be used to do work? How would you use it to drive a machine, such as a clock? Braking cars uses large amounts of energy, and doing it by hand is very time-consuming. Can you think of a quicker way of doing this? How many ways do you know of wrecking a car? One way of wrecking a car is to use explosives. In this case, the explosives are activated by a small electrical current.
Stand by. Firing.
That was a ½ kilo of plastic explosives. How do they work? Where does the explosive energy come from? Let's look at a very simple explosion. This is hydrogen, the lightest of all the gases. And in the cylinder on the right, the gas chlorine. The white cylinder contains hydrogen and chlorine mixed together. Add ultraviolet light, and a lot of energy is released. What happened? Here's a molecule of hydrogen. It consists of 2 hydrogen atoms bonded together. Here's a molecule of chlorine, 2 atoms of chlorine bonded together. Add ultraviolet light, and the end product is hydrogen chloride. How is it formed? It takes energy to break a bond. When the bond forms again, the same amount of energy is released. Hydrogen and chlorine. It takes nearly 200 kilojoules to pull a mole of chlorine molecules apart, and roughly 400 kilojoules to pull a mole of hydrogen molecules apart. When the hydrogen atoms react with the chlorine atoms to form 2 moles of hydrogen chloride, 800 kilojoules are released. The net result is that 200 kilojoules of energy are released, very suddenly, as an explosion. Let's look at that again. The hydrogen and chlorine molecules have a certain energy level.